Yes, so good morning everyone and welcome back. I shall be waiting here for 2 more minutes for more people to join, and then we shall start today's discussion. And again, whenever you have any query during the class, please post them on the live chat. All right, so we are starting right now. So today this is going to be the fourth and final part of on properties of Fourier transform, and this is going to be property number 9 and 10. And here today we are going to study two very important properties of Fourier transform that will let us do things that would not have been possible to do otherwise using the previous properties and so on. And if you're talking about the last homework, I shall definitely give you solutions to those, so we shall be able to compare. I mean, later on I shall give you a solution to those, so that you shall be able to compare your own solutions with those. Right, so today we are going to talk about two very important properties of Fourier transform, namely the modulation property and the convolution property. So we talked about convolution earlier, and today we are going to start with the property. So, and if this is the Fourier transform, this is the inverse Fourier transform. All right. Again, if you have any query during the class, please post them on the live chat, so I shall be able to answer your questions. So property number 8, I think it's 8, right? So property number 8, sorry, not 9, 8, I think it's 9. So property number 9 here, that would be our modulation property. This modulation property is also sometimes called frequency convolution property. And so we'll start by discussing something very useful here. Okay, so what we are doing here, we are assuming that we individually know the Fourier transforms of two different signals. So say we individually know the Fourier transform of two different signals. For example, we know that the Fourier transform of x1t is x1 omega, and the Fourier transform of x2t is x2 omega, right? So I don't think there is any problem assuming that. So what we are doing right now, we are trying to find out the Fourier transform of x1t into x2t, right? Fourier transform of this into this. And as we shall soon see that the Fourier transform of x1t into x2t actually is not the product of the individual Fourier transforms, but instead the convolution of the individual Fourier transform with a 1 by 2 pi scaling factor. 1 by 2 pi x1 omega, and then you have a convolution symbol, and don't worry if you have forgotten everything about convolution, because soon everything shall come back, right? So this is the first property we're going to talk about, modulation. And question is, what is modulation? In signal processing, modulation is nothing but when the amplitude of another signal is controlled by one particular signal. For example, look here, very carefully here. What is modulation? I have a question, for example. What is modulation? So if I say what is modulation, so look at this signal, right? Say I have AX2T. Then I can safely say that if A is a constant, then this scalar constant A is responsible for how much amplitude this X2 signal would have, right? This scalar constant A would be responsible for how much amplitude this signal X2 would have, right? So kind of, in a sense, the amplitude of this signal X2 is being controlled by this scalar constant A, right? If A is large, then it would have large amplitudes. If A is small, then it would have small amplitudes, right? That's understandable for any bounded signal. This is quite true. Now, what if I write something like this, X1T? Now I can say that the amplitude of this signal is being controlled by this signal, right? The amplitude of this signal is now being controlled by this signal. This is kind of that A scalar constant here, right? Now instead of being a constant, it is now a variable quantity, which is again, what is it doing really? It is controlling the amplitude of this signal in a sense. So this phenomena, when the amplitude of one signal is controlled by another signal, is known as modulation, right? So in very simple term, modulation is nothing but the product of two signals. So when you multiply two signals, it's called a modulation, right? So this is a modulation, right? When you multiply two signals, right? So if you just multiply this with a scalar quantity, say for example 3, okay, that would be an amplitude scaling. But when you do that amplitude scaling with another signal by means of multiplying it with another signal, then it becomes something called the modulation. Okay, so multiplication of two signals is known as modulation, right? So there are other forms of modulation. This in specific, in specific sense, is known as an amplitude modulation. Okay, right? So when you are modulating the amplitude of one signal by another signal. All right. So let's prove this. I think again, if you have any query, feel free to stop me and ask me a question. So let's do a proof of this, because we need to know where this thing came from, right? So what are we doing? We are trying to calculate the Fourier transform of x1t into x2t, right? Again, one more important thing, the concept of modulation is commutative in nature. So you can assume that x1 is modulating x2, or you can also assume x2 is modulating x1, because ultimately this is a multiplication, right? All right. So we are calculating the Fourier transform of x1 into x2, and by definition of Fourier transform, this is going to be it. Right? So that's the bare definition, right, of this. There is no difficulty understanding any of it, right? So if x1 into x2 is the signal, then of course that's the Fourier transform of the signal, right? So we are kind of trying to show that this is true, right? All right. All right. So now look at this one, and what is x2? I can go back and I can say x2 is the inverse Fourier transform of capital X2, right? x2t is the inverse Fourier transform of x2 omega, and when that's true, then I can write something like this. And again, if you feel anything to be very difficult, feel free to ask. Okay, we have another integration here, 1 by 2 pi. I have x2 omega e to the power j omega t d omega e to the power minus j omega t dt. All right, that's the definition of the inverse Fourier transform, right? All of you know that, right? So what did I just do? So instead of writing x2t, I wrote the inverse Fourier transform of x2 omega, right? That can be written. Now, don't be intimidated by the double integration here. We just encountered a double integration here, right? Don't be intimidated by that. So yeah, double integrations we can handle here easily, okay? Because these are very special kinds of double integrations. And again, we shall see what techniques we need. Now, one important point to note here is that after doing this integration here for the inverse Fourier transform, after doing this integration, the result is in terms of t, not in terms of omega, right? So this omega is nothing but a dummy variable as far as we people are concerned, right? This omega is a dummy variable as far as we people are concerned, because this is going to be treated like a definite integral sort of, and after doing the integration, omega will be replaced by the upper limit and lower limit sort of. So only t will be remaining as a variable. So omega is a dummy variable, right? So omega can be replaced by something else, namely, for example, so instead of writing omega, so what I'm writing is so I did not write omega here. And there is a reason for that. What is the reason? The reason is that I already have omega as some sort of a variable inside this integration, right? So I cannot introduce the same variable here because that will change the result, right? Because it was xt, try to understand, it was x2t, right? I cannot write omega here because otherwise this will interfere with this integration, right? But in any other sense, this should not interfere with this integration in any way, right? But the thing is, if we did write omega, then this would have interfered with this integration, right? Because this has a quantity that associates omega with it, right? So that is why we're not writing omega, because again, we have the freedom of choosing what variable I want here, because that's just a dummy variable, right? Variable for the integration, because after doing the integration, the result will be in terms of t, not in terms of omega, not in terms of theta, not in terms of any of these, right? And as such, this is not anything difficult, right? Again, if you have any query or any difficulty understanding anything, feel free to ask, right? Now let me write the next line. Again, if you are uncomfortable with any of the things that I write, please feel free to ask. Now I am pulling this 1 by 2 pi outside. Of course, that's a constant. I can always do that. Now I have two integrations. Now here we have double integrations, but don't be afraid of double integrations here. Don't be intimidated by them, because we are here to deal with them properly. Okay, so I have x1t, and then I have x2 theta e to the power j theta t, and we have d theta, and then we have e to the power minus j omega t, and we have d theta dt, right? That's the double integration we have. We just wrote everything combined. But do tell me if this is understandable for you or not. I mean, there is nothing that we have done here is out of ordinary here. All right. Now how on earth were we able to actually pull this inside this? Because try to understand, we could put this x1t inside this integration, because what is the variable of this integration? The variable of this integration is theta. So this is, as far as this integration is concerned, this is a constant term. So this can go inside this integration, right? Similarly, this can also go inside this integration, because this has got nothing to do with theta, right? Because for this integration, theta is the variable, so t, omega, these things are considered constant. So this can also go inside. That is why we have a term like this. We have an expression like this, right? So again, don't be afraid of this double integration, because we are going to treat this quite nicely. So in any case, I mean, I think you understood this, right? But again, please feel free to ask if you have any query at this point, because this might turn out to be one of the easiest discussions if you can properly understand what I'm talking about here, right? So with that said, let me pull another trick. Let me pull another trick. Now try to understand that what we are doing here is called the changing the order of the integration, right? So in double integrations we often do change the order of integration, right? Now try to understand. So we have to once do the integration with respect to t, and then we also have to do the integration with respect to theta, right? So this integration, this internal integration is associated with this theta, and this external integration is associated with t, right? So when we carry out the internal integration, this one, okay, we carry out the integration with respect to theta, right? And when we carry out the external integration, we do the integration with respect to t, right? But look carefully, look very carefully when we are doing the integration, right? Look very carefully when we are doing the integration with respect to theta, right? What happens is we can do this, because whenever we are doing the integration with respect to theta, let's change the color if we could. Okay, so let me change the color for a few things here, so that actually you have better understanding of what I am saying here, because this needs to be understood properly, and I personally believe that you have very lackluster knowledge of double integrations. Correct me if I am wrong. All right. So what we just showed you using two different colors is that whenever I am doing the integration with respect to t, this entire integration denoted in this blue color is treated as a constant. Try to understand. This entire integration denoted in the blue color is treated as a constant, right? Because that has got nothing to do with t, as far as that particular integration is concerned, right? So we can do something called change. We can change the order of integration. We can now pull this integration backwards and do something like this. This is called changing the order of integration. Again, feel free to ask if this is not clear, because this is not easy either. Yes, you are very correct. So one of you are asking, okay, we are saying that this is independent of t and all, but try to look from the perspective of the integration here. From the perspective of the integration, from this yellow one, okay, from the perspective of this yellow integration here, this one, before we have done this integration, this blue one, from the perspective of this yellow one, this blue one is a constant. This entire integral term is a constant, right? So this entire integration term is a constant. We are not thinking in terms of inverse Fourier transform and all, right? And this would not have omega here. Okay, we cannot have omega here, applying the same reasoning as this one. Okay, try to understand. If we did write omega here, what would I have essentially? If I wrote omega here, let's go back. If I write omega here, if I wrote omega here, what would essentially happen? These two will cancel out, right? These two will essentially cancel out, right? Then what would happen? These two would essentially cancel out, right? So this itself will no longer remain the inverse Fourier transform. So if I write this, these two will cancel out, and this essentially will no longer remain the Fourier transform of anything, inverse Fourier transform of anything. So none of these will remain the inverse Fourier transform of anything, right? Right? So essentially what we would have done by putting this omega here is that we have cancelled out one very important term that had got nothing to do with this. Try to understand once again what I just told you. What did I have here? It's an entirely a function of time. Would xt have any omega inside it? It's a time domain signal, right? But if I write this omega, what happens? What happens? Then I have somehow made up a part of xt which contains omega, and that omega is now being affected by this entire term here. You get my point? Xt is supposed to be independent of omega, right? Right? So it is supposed to be a variable only of time, right? But if I have done this, then this term which had got nothing to do with this would now affect the entire term that contained omega here and eliminate that term. So now if I write omega, it can be assumed something like this: we somehow fictitiously obtained the term omega inside this and eliminated that by means of some external action, right? Where in the onset this omega term should not be here, right? This is a function of time. Any function of omega should not be able to affect that, right? The idea is simple. This is a function of time. Any function of omega should not be directly able to affect this, right? Because this is supposed to be entirely a function of time. If any function containing omega affects this, then what does it mean? It means it's also a function of omega, right? It's a function of time, but any function of omega, if it affects this directly, then what happens? What do I mean? What happens then? We understand that then this is also a function of omega, right? But any function of time will be able to affect this, right? This is both a function of time and function of frequency, function of omega, right? Okay. This function as a function of time will be able to affect this. But this function as a function of omega should not be able to affect this, right? So the idea is that this will appear here as a function of time. This will affect this one as a function of time, not as a function of omega. Got this? So if did affect this, if this one affected this one as a function of omega, then I would have to understand that this entire thing is a function of omega, which is in contradiction to what I have here, right? So that is the reason we always try to replace the dummy variables. That is why for convolution we write tau, right? We write tau simply because we don't want to contradict with our variables, right? So we write theta and theta t, and you can write anything in place of omega, okay? And it's going to be d theta. Feel free to ask if you have any query. I believe the rest is understood, right? For the double integration, as far as the integration with respect to time is concerned, try to understand that all the terms represented in blue here are constant. So as far as time is concerned, theta is a constant. So this entire integration is a constant. So what I can do, I can pull this outside and I can treat this internal integration as a completely separate matter, right? And as such, I can happily put a bracket here. Right? So I believe you are getting the hang of it, right? So again, feel free to ask if you have any query. If you have any query, feel free to ask. All right. So we have this. Of course, now again I'm being consistent with my inking here. Consistency is a very important thing in life. Now let's treat this thing as a single function, right? Then what is this integration? This entire integration, what is this entire integration? This entire integration is the Fourier transform of this thing, right? If I treat this as a single function here, of course, which it can be very easily. If I treat this as a single function here, then this entire thing is the Fourier transform of this, right? So I'm saying that this is the Fourier transform of x1t into e to the power j theta t, and we have taken care of the entire integration just by writing this Fourier transform, right? Because if I consider this to be an entire function, then function into e to the power minus j omega t integrated from minus infinity to plus infinity with respect to time, that's a Fourier transform, right? Fourier transform of this thing within the brackets. And then we have d theta outside. Again, feel free to ask if you have any query. I think you got this, right? So let's proceed. Now we know that the Fourier transform of x1t is x1 omega. Then what is the Fourier transform of, we know that, right? We know that if the Fourier transform of x1, if the Fourier transform of x1t is x1 omega, then we know the Fourier transform of this is x1 omega minus a. That's called the frequency shifting property, right? All right, got that, right? So this is going to be x1 omega minus theta. So using the frequency shifting property, right? So we are using the frequency shifting property here. It was, I think, property number 3, I think. All right, you get this, right? Right. But recall, what is the definition of convolution of two signals? Again, these are frequency domain signals, right? What was the definition of convolution between convolution of two signals? The definition of convolution of two signals was this: we have x1t convolved with x2t, and that was defined as integration from minus infinity to infinity x1 tau x2 t minus tau d tau, right? We discussed this in elaborate details on an earlier class, right? So instead of writing t, I can write theta, I can write omega, for example. If this t was omega, or let's write this as t. Okay, so similarly, if we are convolving two signals, so instead of writing t, we would write omega. We can have this integration from minus infinity to infinity. We would have x1 theta, just like tau, it's a dummy variable. Tau is a dummy variable, theta is a dummy variable. x2 omega minus theta. Then again, instead of t, I have omega, and instead of tau, I have theta, the dummy variable, and integrated with respect to the dummy variable. We have this. Right? So from this definition, what do I see? I see that this is nothing but the convolution of x2 omega with So convolution is represented with a star, okay, not with a multiplication but with a proper star, right? So we are convolving two frequency domain signals. X2 omega and X1 omega are frequency domain signals. But since convolution is commutative in nature, I can write 1 by 2 pi X1 omega. And again, what is the significance of the commutativity of convolution? We discussed that in an earlier class on convolution. The class we had on convolution, we discussed all these things. Right. So that is what we have here. So we figured out that the Fourier transform of modulation is the convolution of the individual Fourier transforms. So if I multiply two signals here, then the Fourier transform is the convolution of two individual Fourier transforms with a scaling factor of 1 by 2 pi. We just have put them. So again, feel free to ask if you have any query, because we are going to see a concrete example right now. But before I see the concrete example, we need to tell you a few things. Okay, so that's proved. Okay, so just as a side note, again, if you have any query, feel free to ask. Okay, let's say I have a signal, say xt, and I am convolving this with delta t, the unit impulse. What am I supposed to get? If I convolve this signal with delta t, what am I supposed to get? What am I supposed to get? So you recall that convolution is again commutative in nature. So this can be written, and by that definition, this can also be written by the definition of convolution. Right? This is t minus tau. Okay, right. Now, let me tell you one more thing once again. I said it earlier, but I am saying it again. Fourier transform is the easiest thing when described lucidly. But then again, if you don't practice anything at home, what happens is that very quickly it becomes very difficult. Right? Now you recall integration with unit impulse, right? So you recall that you recall this, right? You recall this integration, right? Delta t ft dt, right? This was f0. So t was replaced by 0 in ft, right? So this is the same integration, right? Except now, what do I have here? I have tau. So as far as this integration is concerned, look very carefully again. I can say something like this. Delta tau, f tau, d tau, that's also f0, right? Same thing, tau is a dummy variable here. But try to understand that f was a function of tau. I replaced tau with 0. So in this integration, I have to replace tau with 0 in this function, because that is like f tau. This is my f tau, right? This is my f tau. So I can also say something like this. If this is x tau, this is x0. So I just replaced tau equal to 0, right? Tau equal to 0, it happened here. So that's the answer. Again, we discussed this in our physical classes, right? So here the answer is when I replace t tau equal to 0, right? That is the result. So technically what do I have? I have xt. So what I wanted to show you is that when I convolve a signal with a Dirac delta, the unit impulse, I get the signal back, right? And that's expected. That's expected. Why is that expected? Because what about this? If you recall anything from our classes on convolution, you would recall something like this. Okay, and this is quite expected because what is ht? The impulse response of a system, right? And we know what is ht convolved with xt. That's the impulse response of the system when the input is xt, right? If ht is the impulse response of the system, then ht convolved with xt is the output of the system, right? To when xt is the input, right? But when delta t is the input, what is the output? The impulse response itself, because impulse response means the output when the input is the impulse, right? Now of course this is the input now, and the input is the impulse, so the output is going to be the impulse response itself. So from that sense, this is h tau as well. Now if you want me to repeat it, I would repeat it slightly in a different fashion. Understand that this integration, the result of this integration, so this is the function here. For the result of this integration, what we do, we replace the variable of this, okay, the entire thing. When is this existent? For example, delta tau has a value of 0 everywhere where tau is not equal to 0, and only at tau equal to 0 this function has a value, and such a value that the integration becomes the same thing when we replace that variable, which is tau, with 0, right? So when does delta t exist? When tau is equal to 0. Just put tau equal to 0 in this, and that will be your result. Okay, that's one of the standard properties of unit impulse. Okay, but again, this is just the impulse response of the system. So this is just a side note again, because we shall need this sooner or later. In a similar fashion, if I have h omega and I do this convolution with delta omega, I have h omega. I mean, convolving with delta does not change the signal. Right. So impulse is also sometimes called the identity of convolution, right? Identity of convolution. All right. In a similar fashion, if I take ht and convolve it with delta t minus a, of course I would have the same integration here, like delta tau minus a. Now of course this is going to be, t is going to be replaced by tau once again, just like our definition of convolution, right? So here, and we have h tau d tau, and again from the property of Dirac delta or unit impulse, we know that the result is just replace tau with a, that is when this thing becomes 0, right, into this. So answer is just ha, right? So this is one of the properties once again. And similarly, if I have h omega convolved with delta omega, so it's just changing the names, it has got nothing to do with Fourier transform. This is going to be, sorry, delta omega minus a, this is going to be h omega minus a. So feel free to post any query that you might have right now, and I will be back shortly, say in 2 minutes. All right. So I think we didn't have any query. So this is directly coming from the property of the unit impulse, right? With that said, now it's time for one question. Aha, did I write this? Yeah, right, absolutely. Hold on. I'm sorry, yeah. I just mistook something here, right? So, okay. This was a wrong thing. Okay, right. Somebody pointed it out. Thank you for pointing it out. What is the definition of convolution? What is the definition of convolution? This is wrong. This one I wrote is wrong. Again, that's the right thing. The thing is, you have to look very carefully, right? I made a mistake, small mistake here, and we were going to pay a big price for that. Yes, the answer is, of course, here I have t minus tau. I'm supposed to have t minus tau. I somehow managed to write h tau here, right? Thank you for pointing it out. Absolutely, you are absolutely right? Because just like the previous one here, I had delta tau here, of course, because I had dt here. Similarly, I have delta tau minus a here, because I have delta t minus a here. But what about this one? I had ht here, so I had to write ht minus tau. Again, I had ht here, so I have to write ht minus tau. That's by definition of the convolution, right? By definition of convolution. So again, by definition of unit impulse, the answer would be this. All I have to do is to replace tau, the variable of integration here, with that quantity which makes the internal argument of the unit impulse 0. So when does this become 0? When tau is equal to a, right? So I have to replace tau with a, right? So that's the answer, h t minus a. All right. And that's the problem of not remembering the formulas. I think you got this, right? Similarly, h omega convolved with delta omega minus a is h omega minus a. Just try to understand that this is identical to this. Just instead of delta t minus a, I have tau. Just instead of delta t, I have delta t minus a. So instead of delta tau, I have delta tau minus a. The rest should be the same. And here I replace tau with 0 in this. That was the answer. And here I replace tau with a. That is the answer. Yes. So when you fail to remember the formula, you have to be very careful about not making a mistake while deriving them. Because if you remember the formula, you will automatically have a feeling that you are doing something wrong when you make a mistake. But when you don't remember the formula, then you don't necessarily always have a feeling that you are making a mistake. And especially stupid mistakes like this, right? And again, feel free to ask if you have any query. And let me tell you, it really makes me happy when I see that you people are actually properly following this. Okay, because otherwise you would never have been able to tell me that it was a wrong thing, right? So with that said, let's jump into a problem. Let's jump into an exercise problem, or rather example problem. So example 1. So we know that the Fourier transform of ut was pi delta omega plus 1 by j omega. And thing is, how do I recall this? Because I have used it way too many times in my life. Okay, the Fourier transform of unit step, for example, right? That is why I can recall it. Okay, and we also know that the Fourier transform of cos at was pi. Do I have a proper space here? Okay, pi delta t minus a plus delta t plus a, right? This is the Fourier transform of cos at, right? All right. My question is, find the Fourier transform of cos at ut. Now, of course, don't even think about treating it as an integration and doing the integration, because even for just cos at, we were not able to treat it as integration. We had to apply duality to some other two impulses, and from that we actually got this, right? And here duality won't also even apply, for example. Okay, and again we also had to figure out the integration of ut by means of duality, right? So yeah, there are so many situations here happening all at the same time, right? So we have this we have to calculate the Fourier transform of cos at ut. So what is cos at ut? Cos at ut, whenever I multiply any signal with ut, what essentially happens is that the signal becomes causal. By that I mean that the value of the signal becomes 0 when t is less than 0. So the signal becomes causal. That is the important thing here to remember. So this was the Fourier transform of non-causal cosine, right? And this is the Fourier transform of the unit step, right? So I am trying to find out the causal Fourier transform of the causal cosine. So what it means is that I am trying to find out the Fourier transform of cos at, and such one, for example, where time is less than 0, the value of this signal is 0, and when time is greater than 0, the value of this signal is equal to cos at, right? So I have made the signal causal. So before t equal to 0, the signal is not non-zero, right? So we are trying to find out the Fourier transform there. And whenever we are doing something like this, we have to understand that we are encountering right now a situation where none of our previous formula would be applicable, right? None of it would work, right? So now we individually have to think that, okay, we have to apply the modulation property. So what is the modulation property? The modulation property simply tells me that all I have to do is to put 1 by 2 pi here and individually take the Fourier transform of cos at and Fourier transform of ut and convolve them. That's the modulation property, right? And take the convolution of them, right? But again, since I have, thanks to this, since I have delta t, this convolution is going to be hassle-free, quite hassle-free, right? So I have this integration here, and what is the Fourier transform here? That's pi delta t minus a plus delta t plus a convolved with pi delta omega plus 1 by j omega, right? So I am again taking care of the pi here, just making it 1 by 2, right? Half. So I have half delta t minus a plus delta t plus a convolved with pi delta omega plus 1 by j omega. So again, if you have any query, feel free to ask. I'm monitoring the live chat always. Right. Now, just like multiplication, convolution is distributive in nature. Okay. Just like multiplication, convolution is both commutative and distributive in nature. So what do I mean by distributive is that just like multiplication, for example, if I say a plus b into c plus d, we write this, right? AC plus AD plus BC plus BD, right? Right? The same goes for convolution. So if I have two signals A plus B, and then if I convolve this with C plus D, then the result is A convolution C plus A convolution D plus B convolution C plus B convolution D. And of course, convolution has higher precedence over addition. So this will be done first, this will be done first, this will be done first, and this will be done first, then they will be added. So convolution is distributive in nature, right? So I think this is understandable. Just like multiplication, it is distributive. This is called the distributive property, right? So with that said, let's proceed and distribute the convolution here. So we have convolution, let's distribute it. We have a half, let's keep the half, okay? And we are convolving this with this. So I have pi delta t minus a convolved with delta, sorry, why did I write t? How on earth did I write t? Okay, none of you really complained, right? Wonderful. Of course, this is the Fourier transform, right? I don't have t, I have omega. So are you people really following? Delta omega plus, then we have convolution of this with this. We have delta omega minus a convolved with 1 by j omega. Then we have a plus, then we have a convolution of this with this, pi delta omega plus a convolved with delta omega. Then we have a convolution of this with this, delta omega plus a convolved with 1 by j omega. All right? So is this, up to this point, is this clear? We just distributed the convolution, right? Now we are looking into this property, right? When I convolve delta t minus a with ht, the answer is ht minus a. All right. So of course now this is my ht, for example, right? H omega, for example, right? When I convolve delta omega minus a with delta omega, for example, I have a situation like that, right? So say, what am I doing here? I am convolving delta omega with delta omega minus a. So this is your h omega, right? So the answer would be simply delta omega minus a. All right? Okay. All right. So with that said, so we have half. So we have pi, and I have delta omega minus a. And again, you can assume this in another way, that we are convolving with delta omega. Or we are convolving this signal with delta omega. So whenever we convolve anything with delta omega, that signal does not change. So in the other way around, this also works. Plus, now we are convolving with this. Now this is your h omega, and we are convolving with this with this. So now the answer would be 1 by j omega minus a. Right? Plus, now again we are convolving this with delta omega. Okay, think about this way, that this is a signal convolved with delta omega. The signal won't change. Pi delta omega plus a, right? And then we have plus, then this is your h omega convolved with this, right? So I have 1 by j omega plus a. All right, that's the entire convolution internally happened. So we have figured out the Fourier transform of the whole thing. So all I have to do right now is just do some more calculation. So I have half, so I am bringing this and this together. So I have pi and delta omega minus a plus delta omega plus a, plus for this term and this term I have 1 by j into, so if I just have them multiplied, so I would have omega square minus a, I mean have them added, I would have omega square minus a square, and on top I have 2 omega. All right, so there is no issue with that. All right, so let's put the half here. So I have pi by 2 delta omega minus a plus delta omega plus a, plus this half cancels out this 2, and this j, 1 by j can be written as minus j, because this 1 can be written as minus j square. So I have minus j omega by omega square minus a square. So that was the Fourier transform of cos at ut. That was pi by 2 all right. So please let me know if you have any query. Right. All right. So if this is fine, I'm giving you the homework right now, and so let's say what we know. We know that the Fourier transform of e to the power minus at ut was 1 by j omega plus a. Of course, a is greater than 0. And right, and Fourier transform of cos bt, I'm not writing, of course I'm not writing a because that will just confuse. That's pi delta t minus b plus delta t plus b, right? So your job is to find the Fourier transform of the product of these signals. So e to the power minus at cos bt ut, right? That is going to be your homework, right? So of course you have to convolve this with this and put a 1/2 pi outside. That's going to be the thing, right? Using the modulation property, right? So kind of this signal is being modulated by this. So with that said, let's jump into the convolution property. Okay. What am I writing? Absolutely. Yes. All right. So now let's jump into the property number 10, which is the convolution property. Okay. So let's talk about the convolution property. So the idea is the same once again. Okay. So we are saying that the Fourier transform of x1t is x1 omega and the Fourier transform of x2t is x2 omega. Then what is the Fourier transform of convolution of x1t with x2t? The answer is the product of the Fourier transforms. Okay, now try to see this, try to understand what happened just here. So if I have, in the modulation property we had a multiplication here that resulted into a convolution here, and in the convolution property we have a convolution here, so that would result into a multiplication here. And from the concept of duality, this is what should happen, right? From the concept of duality you can understand this is what should happen, right? But let's prove this anyway. And let's say, as from a signal processing perspective, this is quite literally the most important property of Fourier transform, because this is going to give you the opportunity to apply Fourier transform on systems, right? You shall be able to analyze systems, and very soon today we are going to solve electrical circuits through Fourier transform, and you shall see that things that you learned in your circuit theory classes, okay, are quite relevant here. Okay, so what we are studying, again, I told you in an earlier class, in your physical classes, that this subject is going to be a generalization of what you studied earlier, right? In your earlier subjects. This is going to be just a generalization of that. So this is what we are going to see right now. Today we are going to solve circuits with Fourier transform, but the things will surprisingly look very familiar to you, right? So again, what is my problem here? I am finding the Fourier transform of x1t convolved with x2t, right? So I am calculating the Fourier transform of x1t convolved with x2t. And again, feel free to ask any problem, any query that you might have. Okay? So this is by definition going to be minus infinity to infinity, this integration from again the Fourier transform of this e to the power minus j omega t dt. So that's the signal we are calculating the Fourier transform. That's by definition, right? So now here we are writing this, and again quickly we are going to encounter a double integration, because how is this defined? How is the convolution defined? The convolution is defined through another integration, right? And what is that integration? X tau, okay, and sorry, not x tau, x1 tau into xt minus tau d tau, right? And we have e to the power minus j omega t dt. Now again, we can keep this t here, because the important point to note here is that this is not going to affect this term here. This is not going to affect this term here, because simply it does not directly cancel anything out, and as such, as far as this one is concerned, this integration is concerned, the variable of this integration is tau, right? So this term is unable to affect this in any case. That's quite understood, right? Right? Now again, I should have used a different ink to denote different things. So let's use a different ink. So I'm using different inks to show parts of the integration that are independent from each other. Again, this is a double integration, but this part of the double integration represented in blue is irrespective of the part of the integration that is represented with yellow, right? That's a double integration, but now we can interchange the order of integration here. We can understand that when I integrate with respect to t, this integration with respect to tau is treated as a constant, because whenever we are integrating with respect to t, any integration with respect to tau will be treated as a constant, and this is a function of tau, solely a function of tau. This is again independent of, yes, absolutely. So yeah, in signal processing, if we had a very huge class on signal processing, and if we could discuss many things, you would see that convolution is closely related to something called correlation, okay? And and while in the class on convolution, I discussed that the output of a system can be calculated by convolving the input to the impulse response of the system, right? But I never proved that, did I? Try to understand. So I showed you a demo, like the violin being played in a hallway like that, something like that. We discussed mathematics, we discussed many things, and I said that if we have a signal, okay, as the input to a system, and if we know the impulse response of the system, the output of the system is the convolution between the impulse response of the system and the input to the system. But this I never proved, right? I never showed that for an LTI system, the output can be calculated as the convolution of the impulse response and the input signal, right? This I never proved, because that proof is kind of beyond the scope of this course. And if you really are interested in that proof, how that really happens, again, in my personal opinion, this makes your idea even more concrete here. So I would need 2 separate classes for this, like 2 hours discussion entirely, to prove that the output of a system can be calculated by convolving the impulse response of the system with the input. Okay, that property can be proved, but I need a 4 hours class, like 2 classes worth of 2 hours each, right, to prove that. So that's due to those reasons. I mean, this is kind of beyond the scope of this. And yes, the convolution we are talking about is actually known as Dirichlet convolution, right? Actually, Gustave Dirichlet did really work on many features of Fourier transform, right? And again, when Joseph Fourier actually invented Fourier transform, he did not even have Fourier series. He did not even have a concrete idea of Fourier transform. In fact, we get Fourier transform mostly because of Gustave Dirichlet, not because of Joseph Fourier, right? Fourier did invent Fourier series, most of the part, and laid foundations of Fourier transform. But the way we study Fourier transform today is largely due to Gustave Dirichlet. With that said, right. So with that said, let's look into the double integration here. Whenever we are integrating with respect to t, okay, anything that has got nothing to do with t will be treated as a constant. namely this integration, okay, which is being done with respect to tau, will be treated as a constant, and this function, which is only a function of tau, not a function of time, will also be treated as a constant. So I can do that integration after I have done this integration, right? So what I can do, again, I can change the order of integration here. Instead of doing this integration later, I can do that first and then do this integration. So let me explain what I just said. So I can do this integration first, and again, this is quite a standard procedure. Okay, and then we would so this integration will not affect the terms I represented in blue ink. Right? So this is called changing the order of integration. And again, if you have any query, feel free to ask. In many books on advanced signal processing, you have an entire chapter on convolution and correlation. Right? And if you do a master's degree on signal processing, you definitely learn that. In any case, I think this is understood. And if this is understood, let's look at this one. Okay, again, I'm using different inks to denote the separate things here. Okay, so what is the thing that I represented using yellow ink? That's nothing but the Fourier transform of x t minus tau. Right? This is what I represented in yellow, is nothing but the Fourier transform of x t minus tau. Right? Just like x t minus sorry, is it just going to be x? What am I writing? Really, I'm disappointed with myself. So this is going to be x2. This is going to be x2. This is going to be x2. Right? All right. So now we already know something like this. We know that if the Fourier transform of xt is x omega, then the Fourier transform of e to the power minus j then the Fourier transform of x t minus a equal to e to the power minus j omega a x omega. All right, so please let me know if you find this difficult to understand. Right? I think I haven't mistaken the sign here. This could be plus. Let's see. That's unfortunately the problem again with me. So let's write this, right? So what is the Fourier transform of x2 t minus tau? Again, let's write this. This is integration from infinity to minus infinity to infinity. So I have x1 tau, and this is going to be the Fourier transform of x2 t minus tau, treated as t minus a, something like that. So that would be, so for example, that would be x2 omega into, so that's the time shifting property, right? E to the power minus j omega tau. Right? J omega tau, and we have a d tau here. So please let me know if there is any problem that you think there is. Right? So now I can bring this outside I can bring this outside, because throughout this integration tau is the variable, omega is a constant, right? So this can go outside. So I have x2 omega outside, and inside this I have this integration. Now look again very carefully that this is not independent of the integration anymore. Although this entire thing came from this Fourier transform, okay, this is no longer independent of the integration, right? Because this has tau in it. So I have x1 tau into the power minus j omega tau d tau. What is this? Tau is again a dummy variable. You could write t here, right? Tau is again a dummy variable. It could write t here. Yes, there are so many things, and for one of you, those who are talking about Dirichlet convolution, yes, you are right now talking about the discrete version of Dirichlet convolution, yes, and the periodic convolution here, right? Periodic Dirichlet convolution for discrete version of that, right? So yes, that is used in digital signal processing for band limited signals, and there are so many things, right? It's called periodic convolution, what you are talking about there. Okay, for discrete time signals. All right. And we are talking about continuous time signals here. Yes, that also exists for continuous time signals. So what we are talking about, namely, is called periodic convolution. We are not talking about periodic convolution here. Okay, okay, let's just call it convolution and be happy with that. So again, look at this term. This tau is a dummy variable, right? And since this tau is a dummy variable, I can write t and I can write whatever I want. So if I write t, it immediately prompts us that this is nothing but the Fourier transform of x1t, right? So that's going to be our x1 omega, right? And this is going to be just, since this is multiplication, right? So this is going to be x1 omega, x2 omega. So we have just again proved this entire thing. So what happened here? Let's go back, and we have seen that the time domain convolution of two signals is giving you a multiplication of the Fourier transforms in frequency domain, right? Like that. Now this has very big implications, very big implications. So in order to understand the implications here, we shall have to look into our own personal domain, right? Like electrical engineering. So let's say examples. Now in examples, we shall soon see that this is quite, you people are actually quite familiar with what I just said here. Okay, so before examples, let's talk about LTI systems. Right? Let's talk about linear time invariant systems. Say I have an LTI system here, and again we discussed this in an earlier class, right? In much broader details while talking about convolutions. Okay. Right? And if the impulse response of the LTI system is ht, and if the input to the system is xt, then the output of the system can be calculated as a convolution between ht and xt. We people know that already, right? Now, in that sense, if the Fourier transform of the input is x omega and the Fourier transform of the impulse response is h omega, then what is the Fourier transform of the output? It is the Fourier transform of the convolution of ht and xt. Then this is going to be h omega into x omega, just like that, because after Fourier transform the convolution becomes a product, right? So that's the most wonderful property here. So instead of doing this convolution, what we can do, we can multiply these and take the inverse Fourier transform to get back to yt, right? And you people have probably done this with Laplace transform earlier, right? So again, the way we study Laplace transform in our electrical engineering classes as Laplace transform, we consider Laplace transform to be kind of a superset of Fourier transform, but that's not really actually really completely true. But in any case, you understand this, right? So this is the term we often use to represent this. Now, of course, with that said, since this is at our hand, so we understand that the Fourier transform of the output is representable as a product of the Fourier transform of the impulse response and the Fourier transform of the input. So with that definition, the Fourier transform of the impulse response can be defined as the ratio of the Fourier transform of the output to the system and the Fourier transform of the input to the system. Right? Do you understand what I just said? Right. That's simple division. This division is now happening simply because of the fact that this was just a multiplication, right? Not a convolution or anything like that. Right. So again, try to understand what I just said here. Right. Now look very carefully that h omega, x omega, y omega, these are all complex quantities, right? So since they are all complex quantities, I have x omega as something like x omega angle x omega, something like that. That's a representation, simple representation for a complex number, right? So this is just like writing. So say if we have a complex number like z, for example. So if we have z, which is, say, for example, x plus jy, then this can be written as root over x square plus y square e to the power minus j tan inverse. So e to the power j tan inverse. Yeah, e to the power j theta, say, where theta is tan inverse y by x. Something like that. So let's say tan inverse y by x. Just tan inverse y by x. Something like that. Okay. So what is this? It is theta, the phase angle of this complex number, right? So complex numbers are represented as a point on the coordinate plane. So this is mod z and this is angle z, right? So this is the representation we use in electrical engineering, right? Right? So this is called the phasor representation of a complex number. Okay. So using the phasor representation of a complex number, if we represent everything like that, then I have y omega as mod y omega angle y omega. Okay. And what is this angle again? Tan inverse imaginary part of this divided by real part of this. And similarly h omega is mod h omega angle h omega, right? And again, with that said, what is the output then? What is the mod of the output? So mod of the output is going to be the mod of x omega and h, let's say the other way around, the mod of h omega x omega. All right. And from the concept of complex numbers, we know this can be written as mod of h omega and mod of x omega individually, right? Got it? So I can say the mod of h omega is nothing but the ratio of mod of y omega and mod of x omega. And similarly, angle of y omega, so that's a complex number again, y omega. So angle of y omega is going to be the angle of h omega x omega. And from the concept of argument of complex numbers, this can be written as angle of h omega plus angle of x omega, right? You can understand that, right? So I can say h omega, angle of h omega is equal to angle of y omega minus angle of x omega, right? So we have these two, this one and this one, right? We have these two at our hand. So what really is h omega? So h omega is such a function that has an amplitude that is represented by the ratio of the amplitude of the output of the system to that of the input of the system. And h1 is such a complex number, h omega is such a complex number that it has a phase such that this phase angle is nothing but the difference between the phase angle of the output of the system to that of the input of the system, right? So h omega determines how much amplitude will be scaled by the system and how much phase angle will be introduced in the system. So from the input and the output perspective, input-output perspective, what is the difference, what is the ratio of the amplitudes of the output and the input, and what is the difference between the phase angle of the output and the input, are all going to be determined by h omega. And again, I told you earlier that when I excite a linear time invariant system with a sinusoidal input, then in the steady state the output is also a sinusoidal signal, right? Only thing is that the amplitudes and the phase angles will be different, right? You already know that, you did do circuit theory and so on, so many things. You know, when I excite a system with a sinusoidal input, the output is also sinusoidal in the steady state. We're discussing steady state. We shall later on learn what I mean by steady state. But for the moment, say we're talking about steady state. So after enough time has elapsed, okay. So when I excite a linear time invariant system with a sinusoidal input, the output is also sinusoidal, right? And only difference will be in the amplitude of the output and the phase angle, okay? So the ratio of the amplitudes to of the output to the input is determined by the amplitude of h omega, and the phase difference between the input and the output is determined by the angle of h omega. So with that concept, now from the concept of Fourier transform, we understand very simply that any signal, as long as it is bounded and it satisfies the other Dirichlet conditions, it is guaranteed to have a representation in terms of sinusoids, right? Maybe infinitely many sinusoids, but yes, it has a Fourier transform representation. So any signal, as long as it is bounded and it has a finite number of finite discontinuities and so on, then the signal has a Fourier transform representation, which means the signal is representable in terms of sinusoids of different frequencies, right? And the output in that sense is also will be representable in terms of a composition of sinusoids of different frequencies, except for different frequencies the sinusoids will have different amplitudes and different phase angles based on these two functions. So let that sink in, what we just said here. The idea is that the output of a system for a linear time invariant system can be calculated by means of convolving the impulse response of the system with that of the input to the system, and that same thing results into a multiplication in the frequency domain, right? That convolution results into a multiplication in the frequency domain, and that actually lets us do slightly more complicated calculations in an easier fashion. So let's see electrical examples, slightly more electrical examples. So let's talk about electrical engineering examples, right? So let's talk about a simple thing, right? Let's see, and these things will be very clear once we understand what we are talking about here. And let's not talk about resistor. Resistor is a simple static system, right? We don't worry about that. But we can happily worry about a capacitor. Right. Now there is a kind of a convention for me For example, if I have this is representative of an ideal DC source. This is representative of an ideal DC source. If I write this is representative of an ideal AC source. And if I write this is kind of representative of an ideal signal source. So ideal source, for example, if it is exciting the system with voltage, I'm considering 0 series impedance. Okay, so yes, ideal. So I have an ideal signal source. So it could be any signal per se, and say this is the capacitance of the system, right? So if this is the capacitance of the system and the input to the system is, for example, this voltage here. So for example, I'm considering this to be Vt, and the current of the in the system is It. These are all functions of time, right? These are all functions of time. This is capacitance, right? So we know the definition of capacitance, right? We know that capacitance is represented as, right, rate of change of charge in the capacitor with respect to voltage. Okay? So it is the unit rate of so that is what it is, right? So we can write down C is equal to dq dt and do this simple school level mathematics, and from that line we can write dq dt equal to C dv dt. So this went to the left hand side and we just interchange the sides, right? So there is no problem with that. So what is dq dt? So what is dq dt? Dq dt is a rate of change of charge with respect to time. This is known as current, and C, and this is the derivative of the voltage. So this is the relationship for a capacitor, the current voltage relationship for a capacitor, right? So the current through a capacitor is determined as C into the time derivative of the voltage to the capacitor, right? So there is no problem with that knowledge, right? There's absolutely no problem with that, right? So you people know that. Now what if I apply Fourier transform on both sides? Now we are going to this. What if I apply Fourier transform on both sides? So I have Fourier transform here. So applying Fourier transform on both sides, what do I get? I have C is a constant, so it goes beyond the Fourier transform. All right. So if we say that the Fourier transform of It is I omega and the Fourier transform of Vt is V omega, it is this, right? Then what about this Fourier transform? So this is I omega, okay, and this is equal to C, the Fourier transform of derivative of Vt, right? What is that? If the Fourier transform of xt is x omega, then the Fourier transform of x dash t is j omega x omega, right? We know that from the time differentiation property of Fourier transform. So now we have this into j omega v omega, right? Simply from the time differentiation property of Fourier transform, right? So with that said, if this is the input, then this is the output of the system, right? Do you understand what I just said? If this is the input, this is the output of the system. But again, if we try to calculate something like this, voltage as a function of frequency divided by current as a function of frequency, what do I get? I get 1 by j omega c, right? This is what we call the impedance of the system. We represent this as z omega. So this is the capacitive impedance, not the capacitive reactance, but the capacitive impedance. And capacitive reactance is just the mod of this, so without the J. Reactance is, for example, right? So that is what it is. Now you will soon realize that whatever we just learned so far, by virtue of, again, how on world we were able to divide this, because of the same convolution property, right? Right. I hope this and right. So that's how wonderful this is, right? So this all is associated with Fourier transform. Now you understand that this is something you studied in your very first year, right, in basic electrical engineering. But the basic electrical engineering requires Fourier transform, surprisingly, something that you are studying right now, okay, in greater details. So hopefully it will make it understandable that whatever we studied so far, painstakingly studied, like for the last, how many classes has it been? Like it has been like 8 classes maybe. Okay, so far on Fourier series and Fourier transform, we have been discussing all these things. This all led to this point where we proved a very simple thing that apparently was very easy. Okay, or maybe not so much. We assumed this, right? Okay, with some vague assumptions and so much. But right now we see that this is quite related, right? This is quite related. This is the impedance. Let's talk about a inductor then. Let's talk about a simple inductor. Again, I have a signal source. Again, ideal signal source. Let me again explain the term, what I mean by ideal signal source. Okay, it's a voltage source I am saying. Okay, so ideal voltage sources have zero series impedance. Okay, so it is not dropping any voltage internally. That is ideal. And once upon a time I used to teach circuit theory. Circuit theory used to be my favorite subject once upon a time. I mean, it still is, but yeah, I don't teach it anymore. Yes, I shall explain your question before I explain this, don't worry. And I am master of bad drawing, as it seems. Acha. So now, one of you are asking, I mean, why do I represent this as a capital letter? Of course, the first thing would be to distinguish this, right? So after transforming, we use a capital letter to represent that this is in the frequency domain. That's one of the notations. In pure mathematics, this is the notation. The Fourier transform is of xt is given by x tilde omega. So x tilde omega. Again, let me ask you, which symbol do you like? Do you like to write a capital X omega, or do you like to write x tilde omega? This is a better symbol for electrical engineers. For engineers overall. So we use capital letters to represent functions in the frequency domain. So this omega is frequency, right? And this is, of course, yeah, uppercase letter, capital letter, right? Capitalist society. So yeah, this is a tilde symbol. This is used in pure mathematics. So if you refer to any book on pure mathematics that deals with Fourier transform, I can assure you, you won't understand anything. Okay, because their perspective is completely different. This is studied as a part of measure theory and complex analysis. A combination of those things. Okay, so you won't understand anything, because I don't understand anything. So that's the thing here. So this is the symbol there I have seen them using, and their definition of Fourier transform is also slightly different from ours. So with that said, that's the thing you asked, and that's the answer. But no one is stopping you from inventing your own symbol, right? The funny thing is, no one really published the work Joseph Fourier did in his lifetime. So as the story goes, okay, he earned some money, and quite a lot of money, and he earned a real estate by fighting in the army. And after retiring, he actually earned, and in army you retire quite early, right? You understand that. So he got got some big estate and lot of money. And before joining the army, he did all this research work, right? And nobody wanted to publish Joseph Fourier's work. So he came back from the army, and with his own money, he published his own research papers. But still then, no one really understood the significance of Fourier series and Fourier transform. Okay, no one really, no one could fathom the idea of this, right? So later on, people really, this Fourier series and Fourier transform came into attention when people actually really needed to analyze things in frequency domain. Then it came into attention, but by that time, Joseph Fourier was long dead. So yes, that thing. So you can invent things, you can invent your own symbols, but people might not recognize your symbols. They might recognize your symbols, recognize your invention and everything, but by that time, you would probably be long dead. And this has been the same throughout history. For many mathematicians, for many people, their significant contributions in the fields have only been recognized after they are dead. They were dead for a long time, right? In any case, for an inductor, for an inductor, ideal inductor here. Again, we are considering ideal situations, like involved everything is ideal, right? As if, right? So inductance is defined as rate of change of magnetic flux with current. So if I change the current through an inductor, how quickly or how slowly the magnetic flux induced in the inductor changes. And that is how we define inductance. And from that, you can do a little bit of mathematical shenanigan here, and you can write d phi dt and dt di. Okay, right? And we happily sometimes cancel this out and say d phi dt, d phi di, right? But this cancelling that is occurring here also has a very huge complicated mathematics in it, right? That we can cancel this dt happily, right? Yeah, there are too many mathematicians in mathematical history who are recognized posthumously. So yeah, so that's like that, and we can bring this to the left hand side. So this becomes L di dt, and that's equal to d phi dt. I'm just changing the so this is d phi and dt, that's equal to L di dt. And on the next line, it would be, what is d phi dt? So this is the rate of change of magnetic flux with respect to time, right? And Lorentz and Faraday told us that this is the induced EMF, right? This is the induced EMF in a coil. Induced EMF in a coil is the rate of change of magnetic flux to that. So that's the voltage, that's Vt, right? So that's the induced EMF. And this is L ddt of it. So that's the voltage current relationship of a capacitor, right? You people already know that as you are electrical engineers, right? Now we can apply our happy Fourier transform, right? Okay, just one more thing. We are using white ink, right? Let's use white ink. Right, now let's use the yellow one. So apply Fourier transform on both sides. So L is just a constant scaling factor, right? And since Fourier transform is linear, the scaling happens without any issue, right? Again, we know that the Fourier transform of this is V omega, right? Capital P. And this is L. And the Fourier transform of it is I omega. So Fourier transform derivative of it is j omega I omega, right? So again, V omega divided by I omega was j omega L, and this is the inductive impedance, right? So this is z omega here. Again, this is inductive impedance, not the inductive reactance. Again, inductive reactance will be just the mod of this. So omega L. Inductive impedance, right? So I believe by now you understand that when you write this in an electrical circuit, what are you actually doing? You are applying Fourier transform on the circuit, right? When you write this on an electrical circuit, you are just writing the Fourier transform of the circuit. You are taking the circuit, writing the Fourier transform. That is exactly what you are doing. Right? So now let's solve a simple series RC circuit. Rather not simple, I mean series RC circuit, just it's simple either way. Right. So let's do this. Again, if you find anything difficult to understand here, again feel free to ask. Alright, but so far we have discussed everything. I mean, in our entire subject here, we have discussed everything as inputs and outputs, right? So everything is, I mean, every signal is either an input or an output to something, right? Something like that. So this has to be treated like an input-output system, right? A system that has an input and an output. So in a series RC circuit, what do we really usually consider to be the output? Somebody tell me that first. In a series RC circuit, what do I really consider to be the output usually? Can somebody tell me? Is it the current that we consider to be the output? Of course, this voltage is the input, that's for sure. But for a series RC circuit, what do we consider to be the output usually? Okay, can somebody tell me? V equal to I, no. I mean, what do we really consider to be the output for a series RC circuit? No, not IR. The output we consider usually is the voltage across the capacitor, right? For a series RC circuit, we consider, yes, VR and VC, to be very exact. The voltage across the capacitor is often considered to be the output, and the reason is pretty simple, right? We can show the charging and discharging of the capacitor and so on, right? Right? So with that said, we are going to now treat this as a system, right? So now let's try to understand what I mean by that. Okay, I mean by that, this is what I mean by that. And again, this is just a bit of technicality, but I like to keep the technicalities intact. Okay. Right. So we have a circuit that kind of looks like this. It seems like I cannot draw today. Right, so this is the circuit, right? All right. and here I apply the input, namely the voltage. And what do I measure as the output? I measure the voltage across the capacitor as the output, right? So what do I need to do? I need to pull two lines from the capacitor to measure the voltage across the capacitor. So these two, here I would connect the input, and here I would connect the output. Now if you recall anything from your circuit theory classes, this thing would seem, this kind of a picture would seem pretty familiar to you. What kind of thing is this one? We used to call this thing with a particular name. We used to call this thing with a particular name. So can you recall that whenever we represented circuits like this? So can anybody tell me? So I could answer this very easily, but I want you to recall things. Yeah, it's a Y or something, but what is the general name? It's called a two-port network, right? Two-port parameter network. It's a two-port network. So in a two-port network, yes, it's a two-port network, right? So in a two-port network, we have an input port, we have an output port, right? And that's the discussion in our idea here. So in our idea, we have a box representing a system, right? And we have input like that, output like that. But can you really send a signal through just one pin? No. You, in order to send xt as an input, if it's a voltage, right, it needs to appear across two pins, right? If it's a current, it needs a return path, right? So if I just write a single arrow, it actually means that I have two lines, okay? One for the signal going in and one for the signal coming out. Because if the input is a voltage, it needs to be applied across two pins, right? If it's a current, then it needs to go in and come out. It needs to have a return path, right? So this is the diagram we draw, but in reality we have two pins here and two pins here, right? So we shall apply the input across these two pins, and we shall apply the output across the two pins. We shall check the output across the two pins here, right? As far as electrical circuits are concerned, so this representation is nothing but a two-port representation. So this is the input port and this is the output port. Input port, singular. Input port. These two pins make up this one single arrow here. These two pins make up one single arrow here. So we feed the input across these two pins and we measure the output across these two pins, right? So this is the input arrow and this is the output arrow, for example, right? Because in order to put a voltage source, we need two pins, right? In order to put a current source, we also need two pins, right? So this arrow is actually representative of these two pins. I think you understand this by now, right? So with that said, I am applying the voltage here, which is an ideal voltage source, rather ideal signal source, right? And we are measuring the output voltage here. So at this point, we are measuring the output voltage. Let's call that voltage across the capacitor, right? This is the voltage across the capacitor. This is the input voltage, call that Vt, and the current that is going in is It, and there is no problem with this, right? Right? So what is the potential drop across the resistor? This is R into It. That is the potential drop across the resistor. What is the potential drop across the capacitor? We have represented that as VCT, right? C is in subscript. And this entire voltage is equal to the voltage across the input, that's Vt. This is Kirchhoff's voltage law. This is applying KVL, Kirchhoff's voltage law, right? This is KVL. Now what is the current that is going through the inductor, capacitor? The same current that is going through the resistor, right? The same current that is going through the resistor is also going through the capacitor, right? And from the capacitor's definition, we know this, that current through the capacitor would be equal to C derivative of the voltage to across the capacitor. So with that said, current through the capacitor can be written as C dV dt, rather dVc plus Vc t equal to Vt, right? So this is the current through the resistor, but this is the same current through the capacitor, and subsequently this is the definition of the current through the capacitor, right? So we have Rc into derivative of current through the capacitor plus current through the capacitor equal to, sorry, plus voltage through the capacitor, derivative of the voltage across the capacitor plus voltage across the capacitor. This is equal to the voltage across the whole RC circuit, right? All right. Now for simplicity's sake, we are assuming a few things. We are assuming RC to be equal to A, just for simplicity's sake, okay? And we are considering voltage to be xt, because that's the input and we represent inputs with xt. And we are considering voltage, the voltage across the capacitor, to be the output, because we consider yt to be the outputs. So with that said, this is going to become A ddt of yt plus yt equal to xt, with these nomenclature in place. Right? Now it's time for our Fourier transform. So what if I apply Fourier transform? So you get the point, right? So we kind of have a generic differential equation, right? Now if I apply Fourier transform on both sides, I have a Fourier transform here, A y dash t plus yt, that's y dash, right, equal to Fourier transform on xt. So if I apply this, what do I have here? So I have A, and the Fourier transform of y dash t would be j omega y omega plus Fourier transform of yt would be y omega, and the Fourier transform of xt would be x omega. All right. Then we can take y omega common out of this, and we would have aj omega plus 1, that is equal to x omega. We're just doing simple calculation here, right? So what is the ratio of the output, Fourier transform of the output to that of the input? That's going to be 1 by 1 plus let's say aj omega plus 1, let's say 1 plus aj omega, right? But from the definition of this, we know that this is nothing but the Fourier transform of the impulse response. Moments ago we have shown that, right? This is the definition of the impulse response, right? Where is it? Yeah, y omega by x omega is nothing but h omega, right? So what is h omega? This is 1 by aj omega, right? Right? So this is the impulse response of the system. So when the input is an impulse, again try to understand, we haven't considered any specific input in this input, right? We are doing this for any input, right? Any valid input, right? We are finding out a generalized expression for any valid input. Now this is the impulse response. So this is the Fourier transform for Fourier transform of the impulse response. So if the impulse response of this series RC circuit is ht, then this is the Fourier transform of that. This is the frequency response, also known as frequency response. So this is this. Then if I apply inverse Fourier transform here, I am calculating the impulse response itself. So I have to apply inverse Fourier transform here. Right? So with that said, I am bringing this a outside. So I have a 1 by a and inverse Fourier transform of 1 by 1 plus a plus j omega. All right. So with that said, this is 1 by a, and of course this is what is the inverse Fourier transform of this? Of course you have to figure out that thing from which this came as a Fourier transform, right? That would be minus t by a on top of e, right? So ut, right? So this is minus 1 by a into t and so on, right? So that's the inverse Fourier, that's the Fourier transform of this, right? The inverse Fourier transform of this. So the impulse response of a series RC circuit is this. So if I plot this very simply, if this is time and this is the impulse response of the system, what is this signal? This is multiplied with ut, so the value of the signal is going to be 0 before t equal to 0, and then it is going to jump up to a value of 1 by a. So when t equal to 0, this is 1, this is 1 by a, and then it is going to gradually decay, right? Because a is of course positive, right? So this is going to be the impulse response of this. So this is 1 by a, right? All right. And just to be very sure that we actually understand what I said, what is a here? A is RC, right? What is a? A is RC, right? So I'm writing, so this is 1 by RC e to the power minus t by RC, right? ut. So what is this RC known as? This RC is known as the time constant. So you also understand this. So instead of writing 1 by a, let's write 1 by RC. Right? So this amplitude is 1 by RC. So gradually it decays automatically. So that's the impulse response of a, so this is the of a series RC circuit. Now we have learned so many things. Now question is, then what is the step response of the series RC circuit? So what is the step response of the series RC circuit? This question essentially means that the input is a unit step, right? Input is a unit step. You understand that, right? So we now know how to calculate this. So we of course have the impulse response of the signal system as 1 by RC e to the power minus t by RC ut, and in order to find out the step response of the system, that is when the input is a unit step, what is the output? If I want to calculate that, the output would be ut convolved with ht, right? The unit step convolved with the impulse response, that gives you the step response, right? Response to a unit step, right? But there is a better way than to do this. What is the better way? We know there is a better way, but you could calculate this, but it will be slightly more difficult. There is a better way. What is the better way? Better way is through the Fourier transform. So we know that y omega is h omega x omega, right? Y omega is h omega x omega. So what is y omega? the Fourier transform of the output. So Fourier transform of the step response. What is h omega? H omega is this. H omega is this. So we did not need to calculate any of this. So h omega is 1 by 1 plus a j omega. So j a omega whatever. So 1 by 1 plus j a omega. All right. Into we have this. And what is the Fourier transform of this? Fourier transform of this. So what is the Fourier transform of unit step? So we know that, which is pi delta omega plus 1 by j omega. Okay. You people are patiently following. It would be over in like 5 more minutes. Okay. All right. So this is going to be y omega. Yeah, this will go over in 10 more minutes. Okay. So now we are multiplying these two signals, right? So let's multiply. So we have pi delta omega into, let's write this down. We have pi delta omega divided by 1 plus j a omega plus pi delta omega plus 1 by j omega into 1 plus j a omega. All right. So we just distributed the multiplication once again. Multiplication here. Now here we are applying a trick right now. What is the trick? We are looking at this. On the numerator I have delta omega. Now delta omega again, it's the impulse function, right? This function delta omega is 0 when omega is not 0. Again, let me repeat. Delta omega is 0 when omega is not 0. So when omega is equal to 1, this is 0. So in the numerator I have a 0. What is the value of this entire thing? 0. When delta omega is 2, 1, anything other than 0. When omega is anything other than 0, this numerator is 0. You get the point, right? When delta omega is anything other than 0, this numerator is 0. So the whole thing is 0. Question is, when is the situation where this whole thing is non-zero? You understand the term, right? When omega is 0, this entire thing is 0. So when omega is non-zero, when omega is anything other than 0, this whole thing is 0. Simply because delta omega is 0 and it is there in the numerator multiplied, right? So question is, when is this entire term non-zero? The answer is, this entire term is non-zero only when delta omega is non-zero. And when is delta omega non-zero? When omega is 0, right? You get the point, right? So this has a non-zero value only when omega is 0, right? So put omega 0 here. If I put omega equal to 0, what do I get? I get just 1 here. So that's going to be pi delta omega plus. Now I have 1 by 1 plus j omega 1 plus j a omega. Right. Right. So with that said, let's simplify this. Again, if you understood this, if you did not understand this, please ask me. And we are now simplifying this by bringing the 1 by a outside. Let me see what I can do. I have 1 by j omega minus 1 by, yes, it would be delta 0. You are right about that. But does that matter? No, it does not matter, right? It does not matter, right? I can write omega because delta will take care of itself, right? Delta itself knows that it has a 0 value apart from omega equal to 0. Yes, it knows that. But we cannot put delta 0 here. Okay, then omega becomes a constant for this particular scenario. right? Let me see what I have here. So I have 1 plus j a omega minus this. So I need to have a here. Yeah, that's the thing here. So I skipped over a very interesting thing here. Let's talk about that. So yes, I thought I can get away with this. Let's do it mathematically. Okay, so we know that yes, that's very fantastic. So if you have any query, again, my point is always feel free to ask. You know this, right? Delta t, I'm doing it with t, you can do it with omega, doesn't matter. It's just a dummy variable, treat it as a dummy variable. Okay, and we have ft dt. What is this? This is f0, right? This is f0, right? This is clear, right, with you? Okay, yeah. So if I try to make some mathematical shenanigan, try to point me out, and if you point me out, I will definitely clear things up. And if I can get away with it, I will get away with it. So I can treat this as this into 1, right? Of course, f0 into 1, that's fine, right? No problem with that. But what is 1? What is this 1? This 1 is this integration, right? The area under the impulse is equal to 1, right? The area under the impulse is equal to 1, that is what it says. But what is f0? What is f0? f0 is a constant, right? So since f0 is a constant, so I'm writing this left hand side once again. So since f0 is a constant, so I'm writing, okay, fine, ft delta t dt. And since f0 is a constant, it can go outside the integration, inside the integration without a problem, right? So I have f0 delta t dt, right? All right. So from this, what do you get? Therefore, and this is valid for any function ft, and since this is valid for any function ft delta t is equal to f0 delta t. Okay. Earlier I showed you convolution, now I am showing you multiplication. Right. So ft delta t is equal to basically f0 delta t. So of course now f omega delta omega is equal to, then of course, okay, similarly rather, f omega delta omega is f0 delta omega. We just replaced names, right? Now you can prove in a similar fashion that ft delta t minus a is equal to fa delta t minus a. Same thing. And similarly, f omega delta omega minus a is equal to f a delta omega minus a. The same thing, I mean, do the same integration here with having no, it does not say ft equal to f0, does it? No, it does not say ft equal to f0, because this integration is there. Okay, and try to understand the fact that this is valid for any function ft as long as it is continuous at t equal to 0. Since this integration is valid for any function ft as long as the function is continuous at t equal to 0, this is treated as an identity, not an equation, right? This is not valid for some particular function ft. This is valid for any function ft as long as ft is continuous at t equal to 0. Similarly, this is valid for any function ft as long as ft is continuous at t equal to a. That's the condition. This does not mean ft is equal to 0, right? This cancellation does not always happen, right? In order to do this cancellation, you have to make sure that this is non-zero everywhere. right? This is not non-zero everywhere, right? Right? So if I say something like this, AB equal to AC, can you just write, does it really imply directly B equal to C? Is it so? Yes, it is so, only when A is non-zero for any condition. Under any condition, if A is non-zero, then this is true, right? Right? And delta D is 0 for every condition other than T equal to 0, right? So you cannot just cancel out delta D. You get the point, right? You cannot just cancel out delta D from both sides, because it's a zero quantity for any value of T other than 0, and for T equal to 0, okay, then only it is valid. So I think you got your point, right? So this is your query, and this is the answer, right? So I think I got that out of the way. So I think this is fine. 1 plus JA omega minus JA omega. So yeah, 1, 2, right? All right. So I'm just simplifying this slightly a bit further. I have 1 delta omega plus 1 by J omega, and I have minus A by 1 plus JA omega. Feel free to ask if you have any query. I'll be happy to answer your questions. Okay? All right. So I promised 10 minutes, but I could not keep the promise simply because you asked me a question, right? I had to answer it. Again, this is partially the reason I am doing it 1 hour early, right? If it were from 12:30, it would be way beyond your lunch time, right? Right. So far, I mean, let me bring this. What can I do? Okay, let's pull this and from here. So I have. So let's go back. So I have y omega equal to, let's copy pasta this. All right, I have this, and of course I want the output. So what is the output? It's going to be the inverse Fourier transform on the whole thing. So what is the inverse Fourier transform of this thing? Yeah, you know that. That's UT, right? Because this is the Fourier transform of UT. And let's write down. This is the inverse Fourier transform of pi delta omega plus 1 by j omega minus this is the inverse Fourier transform of a by 1 plus j a omega. All right. So answer is this is UT, and this will take slightly more effort. For example, I have to divide the numerator and the denominator with a. I can do that. So that gives me 1 by a minus plus j omega. Sorry, Fourier inverse, right? Not Fourier transform, but the Fourier inverse. Fourier inverse, right? Fourier inverse, right? So this is UT minus, of course, this is e to the power minus t by a UT, right? So you can take UT common out of this. So you would have 1 minus e to the power minus t by a, right? So that's the step response of the system, right? So what is the step signal? So this is the step response of the system. So what is the step signal? So a step signal can be assumed to be something like this. Yeah, I will send you the solution of the previous homework later on. So you are familiar with something like this. So if you have a 1 volt power supply, ideal 1 volt power supply, and we have a switch that I turn on at t equal to 0, that will be ideal step input, right? Ideal step input, right? Unit step input rather. So 1 volt applied at t equal to 0. Before that it was open and everything was discharged, imagine, right? So there is a resistor and there is a capacitor, right? So this is what we have derived so far in a general sense. So this is the capacitor, and what are we measuring as the output? We are measuring the voltage across this as the output, right? This is plus, this is minus, right? And this is what we are considering to be output yt, right? So if I now plot this, of course this is going to look like this, and we have reached the end of our page here, and we have reached the end of our discussion here as well. It has been a long discussion because I kind of compacted 1.5 classes here, because from the next step we shall be discussing, and the next class will be on next. So this is how you construct a step input, right? Unit step input, for example. So that's 1 volt applied at t equal to 0. It could be 10 volt, so everything must be multiplied with 10 because it's linear circuit. Fourier transform is linear, everything is linear, right? So if you scale up the inputs, the outputs will also scale up. So right, so I'm plotting this, right? I'm plotting this. So when t is equal to 0, the output is 0, right? Because when t is equal to 0, and again, just let us put the value of this. So this is 1 minus e to the power minus t by RC. So RC is the time constant, right? We represented this as A. So when t is less than 0, the output is 0 because ut is 0. And when t is greater than 0, when t is equal to 0, look carefully, this is 1, then again the output is also 0. After that, what happens? This term gradually decays, and when t tends to infinity, this term gradually becomes 0. So the output gradually becomes 1, right? So the output gradually becomes 1. So this is the output, it gradually becomes, right? And so yeah, the output of the system was so output of the system would be 0 before t equal to 0, and then it will gradually rise. So this is the, and become equal to 1 as time goes on, right? And this becomes equal to 1 as time goes on, right? So this is your output to this of the system, right? All right, so you have seen this. This is the charging of a capacitor. It's a very bad drawing, but you get the point. So in any case, we have discussed quite a lot of things, and we shall discuss quite a lot in the next class as well. Okay. So that will be the end of today's discussion. So I have already given you a homework problem with this, and just take another problem. So your job would be to again, this is another homework problem. Again, why am I giving you all this? So that you have some practice on this. Otherwise, it will be very difficult for you to actually follow the next few classes unless you, practice it. Okay, so question is to calculate the impulse response. Let's create another page. So problem would be, no, the previous plot represents, so one of you asked, does it represent the discharging of a capacitor? No, it represents the impulse response. What is it? So if you give impulse as a voltage input, okay, to the system, what is the output? How does the output look like? So you give one very sharp impulse like input to the system, right? You excited the system with an impulse. So you gave the system an input which lasted for a very small time but had a very high magnitude, and you left the system like that. So the capacitor got charged. Through the impulse, the capacitor got charged to a value of 1 by RC. And then, since there was no more input, because impulse only stays at t equal to 0, after that the value of the impulse signal is 0. So there is no input to the system. So capacitor abruptly got charged due to the impulse to a value of 1 by RC. The voltage of the capacitor across the capacitor had become 1 by RC. Then, since there was no input, the capacitor gradually got discharged. Yes, it got discharged, but not the way you probably would think. It is the discharge happening here, right? But the capacitor got charged due to an impulse. So this is called an impulse charge. Okay, by a very short lasting but a very high value of input, you charge the capacitor quickly, okay, to a value of 1 by RC. But since afterwards there was no input, the capacitor got gradually discharged, and that is how it decayed, right? The output got decayed. So yes, this was discharging in a sense. So your homework would be, for a series RL circuit, consider voltage across the circuit to be the input, okay, current through the circuit to be the output. So this is the voltage across the circuit, and this is the current through the circuit to be the output, okay. Then find H omega, Ht, okay. So impulse frequency response, impulse response. Also from there calculate the step response. So if you do this, it will automatically cement your idea of what we just discussed today. So it was a lot of discussion. So thank you for patiently. So if you have been here for the last 2.5 hours, so I would assume that the subject actually interested you. Okay, but again, this takes a lot of patience to actually properly understand and have a feeling about. In any case, I'll be here waiting for 1 more minute. If you have any query, feel free to ask. Otherwise, we would end the discussion today. Thank you very much for waiting patiently for 2.5 hours. Psychology says we cannot listen to anything patiently for more than half an hour. But you waited here for like 2.5 hours. So thank you very much. And yes, if you plot it, you will have a better understanding. So it's up to you. So the next class would be on Wednesday. Next class would be on Wednesday. So, all right, since you don't have any more questions, so we shall end our discussion today. And of course, we shall not be directly talking about Fourier transforms. Some of you asking what is IT? IT is the current through the RC circuit, RL circuit, right? So yeah, so IT is the current through the RC circuit, RL circuit, right? All right. So you can, in case you have any query, feel free to ask. And on the next class, we shall only be talking about systems and how we integrate our ideas that we developed so far into analyzing systems. So since we kind of have almost reached the end of our course, we are at a 90% of our course. So yes, we have kind of reached 90% of our course, finished 90% of our course. So we shall need like I think 3 more classes at max to discuss a few more relevant things. Okay, how we apply this on systems, and we shall solve quite a lot of problems. And down the way, we shall learn a few more things related to systems, how systems behave, how systems introduce energy and power into the system, into the signals, and like that. We shall talk about amplifiers and any answers. Okay. Something went wrong with my software, and the Zoom did not really work out. The zooming facility did not work out. Anyway, yeah, that is right. All right. So thank you very much. With that said, we'll end our discussion today. Thank you really very much, and we shall see you on Wednesday.